Okay, now let's see problem on block diagram reduction. So here is a block diagram for you, and let me read out the question. Find the transfer function, that is C of s to R of s. You know what is C of s and R of s from the canonical form of the above block diagram. That means this is a way of asking question to find out the transfer function after reducing the block. Now, before going into that, let me tell you something again about the reduction of a block diagram. By reduction of block diagram, it refers to transferring a complex block diagram like this into a block diagram consisting of a single summing point, a single forward path gain G, and a single feedback path gain H. Okay, so this is your canonical form. Now, we have already studied in the last video that there can be, changes can be made at the position of the summing point or the takeoff point before the block and after the block. Okay, based on an objective, keeping something in your mind. What is that? Keeping that this block diagram should reduce to this canonical form. So it's very important that you should have a lot of work that you should do on it, that is practice, I mean. Then only you will be able to understand what must be done so as to convert it into canonical form. Now, sometimes your if you are not properly doing that change in the position of this summing point or the takeoff point, then that particular thing can be complex. It cannot be a simpler one. So it's very important to identify, to select which are all the position change that you need to do. Now, looking at this block diagram, let me explain, or let me have an introduction, give an introduction, a description of this block diagram. As you all know, first of all, let me tell you that this block diagram is in the frequency domain. What's the meaning of this? You have an R of t, but in the question it is given R of s and C of s. I'm just so it is actually the frequency domain R of t and C of t, where C of t is the output, R of t is the input. And this question or this block diagram is totally in the S domain, meaning this G3 is a function, G1 is a function, G2, H1, H2, all these are functions of what? Functions of S. So we know that all these are transfer functions. Now this G1, G2, G3 represents the forward transfer function, while H1, H2 refers to the feedback transfer function or feedback path transfer function. Now, looking at this, you have two forward paths. Say, what I meant by forward path is, if I send a signal from this point, that signal can reach at C of t in two different ways. That is, straight away it can go through this way or it can go through this way. That means you have two forward path. Anyway, this forward path terminology is not frequent in the block reduction technique, while when we go to the next modeling, that is the signal flow graph, this has an immense importance, that is the forward path and the feedback path and all those things. Okay, we will be dealing that when we deal with the SFG. So you have two forward paths and then you have two feedback paths as well in the form of H1 and H2. Now the question is to find out the transfer function. Now before finding, you should get the transfer function from by converting this into the canonical form. So that's the first objective, or in other words, it may be asked something like this. The question can be asked like this: reduce the block diagram and thereby find the transfer function. Okay, all this refers to the same thing. Now, coming to this point, what can we do at this so as to make it so always keep this in mind, right? Okay, now okay, now I'm just analyzing, trying to analyze this. Say, consider this one as I'm marking with a pencil. the part of this. Look at this part. Can you convert this small part into this way, or can you consider this as the canonical form? No. What's the reason? What actually makes this not in this form? The presence of a summer, right? So, some way or other, if you can shift this summer to this direction, to this point, okay, so this summer is the problem. So you cannot shift this to anything beyond this. So there is only one option to shift this summing point beyond G, I mean before G2. Okay, before G2. That is placing this summer before this G2. Okay. Now placing this summer to this point has some challenges. So that's what I'm going to explain. See, I'm using a signal A and B. Say, call this as a small letter A and B. A and B are the two signals passing through this path. Now what happens when it reaches here? This is A into G2. Am I right? So this will be B, right? This signal will be B. What is the output here? So the output here will be A G2 plus B. A G2 plus B. Right. Now, my aim is to transfer the position of this summer to this point. Okay. Even if I transfer this point, I should get AG2 plus B. That's my challenge. Okay. So what's going to be the problem if I sum up with this? If I'm simply shifting here, B also will be having a G2, and my expression is going to be B into G2. That's not what is required. Okay. So first of all, let me show that by just changing this position to this position. Okay. So that can be drawn as follows. Okay. Now, as I told you that I have here is a figure where I have transferred the position of S3. Okay, for the meantime, I have named the summers as S1, S2, S3. It's not necessary. It will be nice if the reason is you must show the step. So you should name the step, what you're doing, or rather the algorithm or the steps you should write. So what you are doing, you must specify. Then only you can draw the diagram. So the first step is changing the summer S3 to the left of S2. Okay, S3. So in order to identify if there are more than one summer, it is best to identify these by such letters S1, S2 and S3. So you can write like this, changing the summer S3 to the left of G2. What I'm doing is, so even if you change, the output that should come over here must be AG2 plus B. Let us see whether it comes here as AG2 plus B. Now what is A? A is actually the sum. So the sum, this is actually the A, right? And this path, this is the signal that comes through this path. What happens to this? Now when it reaches here, this is actually A plus B, right? Now as it passes through this G2, this becomes A plus B into G2, or this is going to be A G2 plus B G2. What is the signal that you require? This is AG2 plus B. That means B should not have a G2, right? Okay, so what can you do? So this B comes over here, it gets sum, so this cannot be avoided. Anyway, the signal that comes to this side will be summed up, and the whole sum is going to get multiplied by G2. Now what you can do is, imagine that you have something like B by G2. Then what will happen? This G2 and G2 get cancelled. Therefore, you will be getting AG2 plus B. So how is it possible? Now, before this B, as B passes through this, if you can multiply this G3, divide this G3 by G2, right? So that is G3 by G2. So this is a change that you need to do in this block. So what happens? So this becomes, so this is already G3. The signal that comes out of the G3 is called as B. Now that signal actually gets divided by G2. Okay, right? It is as if you are multiplying this B by G2, right? So G2, now this becomes B into G2, I'll show it by the pencil. So this is B into G2, right? Now this becomes A plus B G2. Now as it goes through this, sorry, it is B by G2, sorry. B by G2, this is B by G2. As it goes through this, it get cancelled, forming A2 G2 plus B. Okay, hope you understood how to change this, right? Okay, now listen please. So this is actually CFS and RFS. Now what can you do from this? Now the change has to be done on this figure. So this figure has been transformed to this figure by doing this. So hope you understood that there is no even after changing, when you look at this, you are going to get the same signal. So this is what is very important. You can shift the summing point or block anywhere else, provided the output, okay, before changing and after changing should not alter. Now coming to this side, now you can see again, can you convert this into a simple canonical form? Can you consider this this thing into canonical form? No, again the answer is no. Why? What is the reason? The reason is this. Okay, so you will have to think of changing this to so you have a two summing point. When see this scenario we haven't seen previously in when we frame up the loss. That's what I told you as I explained that I mean you will come across different scenarios where you need to apply your logic. Now when two summing points comes together, it is always recommendable if needed to change the summing, so interchange the summing action. Okay, that is, I will explain what it is. Say for example, I have rubbed the previously marked pencil marked writings. Okay, just to explain this. Say imagine that you have a signal coming from G1 as A and this as B. Okay, now this is C. Okay, so what is the signal that comes over here? This is going to be A minus C, right? Then that plus, so this will be A plus B minus C. Okay, now if I interchange this summing, that is I'm going to change this summing input to this summer, right? Okay, and this to this. Okay, so even if it changes like that, that's what I'm going to do. That is, I am interchanging the summing inputs. Okay, there is nothing wrong in writing like this. Say if this minus C is done over here also, and this B comes over here, then also the signal is going to be A plus B minus C. All right, so you will understand when I draw the figure. Okay, so that means even if, that is what I'm going to do is I'm going to shift this to this input to this summer, and I'm going to shift this input to this summer. So you have two summer close to each other. So again it is as if what we do is we will be doing what is done over here is A minus C plus B, and if you change it will be A plus B minus C. It's both are the same. So that's it. That's the logic behind that. So you are just interchanging the inputs of these two summers, and I will call that name. I have used the name. This is S1, this is S2 and S3, and what I'm going to do is interchanging the inputs of S2 and S3. So that's a recommendable way of doing when two summers. So this must be done when two summers comes together. You can interchange the summing, and that's a simple mathematics. Okay, because A plus B minus C is nothing but it is exactly the same as A minus C plus B. Okay. Okay, now the block diagram after interchanging, that's the step 2, interchanging the inputs of S2 and S3. That is, this S2 and S3, this input is transferred over here and this input is transferred over here. So now let us see whether it makes any change. So what the output we require is A plus B minus C. Mind you, I am using the same letters here, A, this is B and this is C. What happens at this point? This is A plus B and this is going to be A plus B minus C, which is exactly the same as the output of S3. That's what we require. So that is enough. So this change will not affect the output of S3. That's what we needed. So now let's see this part. Now this becomes a canonical form, so that you can replace this as a single block with the with the with the with the with the transfer function. We know what is the transfer function of this canonical form: g by 1 plus gh. Why plus? Because it's a negative feedback system. So when you come for the when you come to the transfer function expression, this becomes 1 plus gh, and you can simply find out the transfer function. Now let me find out the transfer function of this. Okay, so I'm going to write the transfer function over here. So the transfer function of this point will be, what is that? The first will be g2 by, now what about the next one? 1 plus g2 h2, right? Okay, so this is the block. This one is this. So you can replace this, the whole thing, by this block. That's in the next figure. Okay, now one more thing is to be noted is, now in the forward path, this also, what can you say about this? So I told you that this is a common point from where these two blocks goes, and these meets again at S2. Okay, so that means, what can you say? This we have learned in the previous video, that is it is equivalent to what? It's equivalent to what? Or it's blocks in parallel, right? This is blocks in parallel, because these two blocks are having the common point at both the side. Sorry, this one. These two blocks is having the common point at these two sides. So this is, what is this? This is a parallel block. So this can be considered as a parallel block, while this is the canonical form. Canonical block, this becomes the parallel block. A canonical block can be converted into this. Now what is the equation for parallel block? Now you can convert this as, so I'm just rewriting that equation as g3 by g2. And how will you do parallel connection? So as shown here, say if you have g1 and g2, the parallel combination will be g1 of s plus g2 of s. In this case, it will be g3 by g2 plus 1. This can also be converted. So this combination, okay, this combination can be replaced by this block. Okay, now replacing, now the next figure is going to be replacing this canonical form and parallel form by a single block diagram. That's in the next figure. Okay, that's step 3. Okay, so here comes the step 3. So I'm just again explaining that. Say you have a parallel block and a small canonical form. Okay, now this canonical form is replaced by this block g2 by 1 plus g2 h2, and this is g3 by g2 plus g1. It's not 1. Okay, this is plus g1. Okay, g3 by g2 plus g1. g3 by g2 plus g1. This is the parallel block. Now replacing that as a single block, you will be getting like this. So you have two blocks, and now what is this? What is this? This is actually your cascade form, right? As you have seen in this diagram. Now you are finding out blocks in cascade. That's the next one. Now combining the blocks in cascade, that's your step. So what is your step 3? Converting the canonical form and parallel block, and converting the canonical form and parallel block in the above figure by a single converting this canonical form and parallel block in the above figure. So almost you must refer the above figure. So based on this figure, you're converting this block into a single block. That is the canonical form and a parallel form into a single block, as shown here. Okay, as shown here. Now the next step is to combine this cascade. So that's your step 3. Okay. Okay. Coming to step 4, what you are doing is you are combining this together, combining these two blocks, that is g3 by g2 plus g1 into, so as we have studied earlier, two blocks when together, what will be the effective transfer function? This will be g1 g2, right? G1 into G2. So using that, you can write this like this. I'm just showing it in a pencil. G3 by G2 plus G1 into G2 divided by 1 plus G2 H2. So you can multiply this. So multiplying, you will be getting this as G3, this G2 and G2 cancels, so G1 G2 divided by 1 plus G2 H2. So that you can replace the cascade into combining the cascade block in the above figure into a single block, into a single block, right? So this is our figure. You need to, if you want, it will be nice for a good presentation. It will be nice if you mark each figures by figure 1, figure 2, figure 3 and refer that figure number. What can you say about this? This is actually the first question, the first part of the question. What was the question? You are to find out the transfer function, but basically it comes around to be the second part from the canonical form. So this is the first part of this question, and this is the canonical form. So this one is the canonical form. Canonical form of this complex block diagram. Now let me tell you that you have GS. What is your GS here? Now here your GS is here. Your GS is G3 plus G1 G2 divided by 1 plus G2 H2, while your H of S is equal to H1, right? Now you can make use of which equation? GS by 1 plus GSHS. Why 1 plus? Because it's a negative feedback system. This is your R of S, this is your C of S. So this is going to be your C of S by R of S. Okay, now just substitute this into G of S to be G3 plus G1 G2 by 1 plus G2 H2, while H of S, take it as H1 of S. So finally you will be getting an equation like this. So that will be, so you may just do it by yourself, substitute and simplify. So you will get this as G1 G2 plus G3 divided by 1 plus G2 H2 plus G1 G2 plus G3 plus G3 plus H2. This is how you should get. Okay, so so simplify in such a way that you get this thing, and this can be put into a single block, and you can call this as, what is this? This is R of S and this is C of S. Okay, so this is your block diagram. Okay, hope you understood this. This is your transfer function, while the canonical form is this. Okay, this is just being represented as an open loop system, but it's not an open loop system. This is a closed loop system. Okay, now there is a problem for homework. You may just do. I will just explain how to do this. Okay, now look at this. You can follow the same steps. So you have an R of S and a C of S as usual. And how many forward path gain? G1, G2, G3. 3 summers you have, and you have a 1 feedback. And as shown in the previous figure that I have marked just by a circle, sometimes the summer can be represented by putting a cross here. That doesn't mean that that's a multiplier. It is again a summer. Okay, don't get confused. Sometimes in the question paper you can see such a symbol that also refers to the summer. It is not a multiplier. Now at times no signs may be given at any of the inputs. Say as we done in this problem, there is no sign, meaning that this has to be assumed to be positive. Okay, similarly at times it will be giving a sign. Okay, if there is no sign, assume that as a positive value. Now this is the block diagram. Now what's the problem? Now how to start with? Now I'll just explain you how to proceed with this problem. Now, when you look at this point, you have a tendency to move this to this side, right? So if you move this, you feel that this becomes parallel. Okay. Now, before moving this, one of the important things that you need to notice, the mistakes that you used to commit is, you may feel sometimes the students may write this as a parallel block. So if it is found to be, if it is really a parallel block, what you can write instead of G3, G2? You can combine this block as G3 plus G2, but you cannot do that because this is not parallel block. Why? The one thing which prohibits it to be a parallel block is this point. If I can move this point either to this side or to this side, the problem is solved. Then you can just simply say that G3 and G2 are parallel. Okay, so it will look like this. See, you have G2 and in parallel you have G3. Okay. Now, if this is the case, only you can convert this into a parallel block, that is G2 plus G3. This is A, assume that this is plus plus. But this is the problem. Now, if I can shift to this point or this. Now, as I told you earlier in the previous video, that it is always recommendable to, as far as possible, if it is able to shift your point either to the left or right of a block, rather than preferring the shift over across this summer. So prefer always the block, because for to change the summer, in order to change the position before or after the summer, you need to take care of two inputs, and that becomes more difficult in comparison to this. So it will be always safe to shift if there is a provision to. But in the previous problem we shifted across the summer because there is no other way. That's it. Now if I change this, this will look like this, right? So this H1 will be going like this. This H1 will be going like this, right? Okay. Now what happens is, I want to see that if I change this, the output that is going through this has to be the same. Okay. So that means, say I'm going to put like this. Okay. Now what I'm going to do is, say suppose this is your A. Okay, this signal is A. What is this signal? This signal becomes A into G2, right? A G2 has to go through this, right? Now what if I have changed means the signal will be coming over, which is coming over here will be A. This has to go through this G2, then only the signal that this feedback requires A into G2, but you are getting only A. So what do you need to do? You need to multiply this by G2. Okay. Now once if you do that, you can convert this into a parallel block. So the next one will be G3 plus G2. Okay. Now you have a okay, you are bringing this point to this, right? So you have a summer here, right? And the summer is coming like this. Okay, this is how it is. Now you have a summer like this, and you have a connection like this, that is G2 H1. Now this is a scenario. Now what's the problem? Now this is going to be the problem, right? Now this can be considered as a canonical form if this can be moved in this direction. Now if this particular signal has to be moved here, that is, the signal is A. Assume that this is A. Now if it moves, it will be having the effect of G3. So this will be G3 plus G2 into A. But I only need A here. So if I am shifting here and I don't want the effect of G3 plus G2, I need to divide this by G3 plus G2. Okay. So you can reduce this into the canonical form, and that can be reduced. Okay. So in this way, you may just approach and find out the transfer function.